I'll begin with a word of prayer. Ahem. 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 I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. All right, so let me try to run through these fast as I can. Find the IOC and ROC for this 3 to the n over n squared times x minus 2 to the power n. So let's see here. They identified that the center of the given power series is 2, that the coefficients were 3 to the n over n squared. I'm on board so far. And then they looked at the R. Is that what we derived? I guess it's what we derived yesterday, isn't it? So but this, you got to be careful with that formula. It only makes sense if what? All non-zero coefficients, right? Are we in that context? We are, so it's good. And so the radius of convergence is apparently 1/3. That makes sense. Yeah. And so you get plus or minus. Now, whoa, flag on the play here. Once you get that this 1/3, that means that the IOC includes 2 minus 1/3 to 2 plus 1/3. So if this is legit, the only reason that this is legit is because of these saying include endpoints. Do these things that I'm not looking at yet below where I'm writing actually indicate that we should include the endpoints? If I plug in 5/3, I've got, what is that? Oh, okay, so this is minus 1/3 to the n. So actually, just cleaning it up a bit, this is the sum n equals 1 to infinity of minus 1 to the n over n squared. Good news, that's the alternating p equals 2 series. Indeed, we should include that left endpoint. Yay. And likewise, the other endpoint, when you sort through it, you missed your power n here, but that's because I cut you off. You get the p equals 2 series. Yeah? So, yep, both of those endpoint series are convergent, so the interval of convergence is exactly what you guys wrote, although the way you wrote it is offensive to me. Sorry, 5/3. I mean, there is a more offensive way to, like, to me, the most offensive way to write it is this. Which is what you were taught as children. Incorrectly. Sorry, this is horrible notation. Like, this is just, and we teach children that this is the right thing to do, right? This is an improper fraction. You need to rewrite it this way. Except that later we're setting you up for the fail in algebra, because if you multiply that by numbers, it does really wrong things. Like, multiply this by 3, what do you get? Multiply this by 3, what do you get? Do you get 6? Do you get 2? I mean, how do you multiply the 3 on that, right? It's a horrible notation. If you put a plus here, it's okay. But this is better. Sorry. Just talking. I would be loved by the elementary school children because I would tell them that half of the things they're being taught to do don't matter. They're like, just leave it like this. It's good. Better in the long run. Okay, I digress. This one here, I disagree. And I don't disagree because what you wrote there is wrong. I disagree because of how you're interpreting this. This is geometric series with a equals to 1 and r equals to 3 times pi x minus 7. So all we need is that the absolute value of r is less than 1, which is to say that 3 pi x minus 21 is less than 1, which is to say minus 1 is less than 3 pi x minus 21 is less than 1, which is to say that 20 is less than 3 pi x is less than 22, which is to say that 20 over 3 pi is less than x is less than 22 over 3 pi. IOC is 20 over 3 pi to 22 over 3 pi. Now, what you wrote was not wrong. I don't think. It's good. But when you're going through the ratio test, right? And you work through this. Now, this is okay. Well, this is not wrong, but also there's a step in here that they left out, right? This is after taking a limit, right? Before they calculated 1/3, they had what? They had actually, back in this other problem, what did they actually have? They had the limit as n goes to infinity of, what was it? It was n squared divided by n plus 1 squared times 3, right? That's what you had before you took the limit as n goes to infinity, and notice that the n squared over n plus 1 squared goes to 1, which left you with 1/3, right? But the fact that before you take the limit, you actually have a ratio of terms, Cn plus 1 to Cn, which is not a constant. That means it's not geometric. In contrast, if they went through the same calculation over there, you should find that the ratio of terms is a constant. Did you guys find that? I erased it, but I think you did. If the ratio of terms is a constant independent of n, before you take the limit, that means it's geometric. So we can fall back on the geometric series result and save ourselves a bunch of trouble. You don't need to check endpoints. The endpoints are not in there. The interval convergence is just the absolute value of r less than 1, whatever that tells you. All right? So it's important to remember where we came from, right? Where we come from? Geometric series, right? That is our hood. Well, it doesn't really work. Anyway. So anyway, I'm just going to start again. There was something here that was a value, but no. Okay, so maybe what you were doing was referencing the inverse tangent, which we derived the other day. If that was the case, bravo, very good. But I want to show you how to start from scratch. And from here, to start from scratch, I would advocate the following viewpoint. G of x equal to inverse tangent of x squared. Focus on that. Find the power series for this, and then use that to piggyback your way to what you're asked to do, because it's easy. Once you figure out the power series for that, you multiply by x cubed, good to go. So one of the reasons I didn't keep what you guys had on the board is you said that df dx was equal to the following. That's not true. It wasn't the derivative of f, which was the following. It was the derivative of the coefficient, the inverse tangent x squared inside the f, right? So that thing that was written on the board before, df dx is 2x over 1 plus x to the 4th. Good, right? Kind of idea, but that's not df dx, right? That's the derivative of a different function, which I'm calling g for our convenience. And, okay, great. Geometric. Sum n equals 0 to infinity, 2x minus x to the 4th to the power n. Here I'm saying a equals to 2x, and r is equal to minus x to the 4th, making the geometric series step. Now let's clean that up. Cleaning this up a bit, n equals 0 to infinity of 2 times minus 1 to the n, x to the 4n plus 1. Great. Now that's the power series for the derivative, not of the function, but of part of the function, right? And so I can integrate to get back what g is. So it's going to be some constant, right? Plus the sum, and I've learned my lesson. I'm going to keep n equals 0 because, anyway, let's not talk about it. 2 times minus 1 to the n over 4n plus 2, x to the 4n plus 2. N starting at 0 means that that series I just wrote down starts at x squared. So if you think about evaluating the series I just wrote down, it's all going to be 0. So if I look at g of 0, what do we get? It's c plus the 0 series, right? What's that supposed to be equal to? It's supposed to be equal to inverse tangent of 0. What's inverse tangent of 0? I heard a 0. I like that. That's good. So apparently this is g of x because the c is 0. And so what am I looking for? I'm looking for f of x. How do we get f of x from g of x? We simply multiply by x cubed. How do you multiply a series by x cubed? That brings up a deeper question. How do we multiply series? Right? I'd like to spend most of the last part of class here talking about that. All right? But I need to wrap this up first here. So anyway, f of x is equal to the sum n equals 0 to infinity of 2 times minus 1 to the n over 4n plus 2 x to the 4n plus what? We had 4n plus 2. We multiply by x cubed. That changes it to a 4n plus 4n plus 5. Right. All right. And there you go. That's how you do that one. Any questions? Okay. Problem 4 is an interesting problem. I gave you this kind of mysterious power series with coefficients Cn, and center 2 has an interval of convergence minus 1 to 5. All right? The first thing you might hope for is that I've given you an interval of convergence which is inconsistent with the given setup, right? If that was the case, you could say, your problem doesn't make sense. I'm not going to work on it, right? But does it make sense? Well, minus 5 is what? It's plus 3 minus 3 from the center of 2, right? So at least the interval of convergence makes sense. All right. And so what you guys did was you figured out that the Cn plus 1 over Cn is equal to 3, what? Generic Cn plus 1. I think you're on the right path here. Well, I'm going to leave this one. Let's go on to the next one. Let's see here. This one we can work. I mean, we'll come back to this eventually, just not today. I have other things to do. I'll let you guys think about that one. I would suggest, I mean, here's a generic advice for it. You need to control the limit as n goes to infinity of Cn plus 1 over Cn. That gives you information about the radius of convergence, which you could kind of already cull from. I mean, you can see the radius of convergence from this, but you also can see the radius of the limit of Cn plus 1 plus Cn as n goes to infinity as it relates to the radius of convergence like we did in problem 1 and we derived last time, right? So you can figure out what the limit is as n goes to infinity of the ratio of Cn plus 1 to Cn as it relates to the radius of convergence here. That means you can calculate the limit of the ratio of the coefficients Cn plus 1 to Cn. Knowing that, you know the radius, you know both that limit, all right? You know the limit of the ratio of the coefficients. So when you look at the next problem, which notice has now as a 3 to the n, you could figure out the ratio test here based on the data that you got for the limit of the Cn plus 1 over Cn. That's a sketch of how to do it. And then you got to fuss about endpoints. I'm not sure what happens with the endpoints right offhand. Okay? But anyway, this one here, we don't need inequalities. There's no, no, I'm sorry, guys. I'm just going to have to pull the plug on your solution there. Because the way to solve this, problem 5 is actually much easier than problem 4 because you're given much less to work with, all right? But the basic way I would guide you to do problem 5 is with a picture, with a number line, all right? Here's the deal. Here's the number line. Where is the center of the given power series? minus 2, right? This has center minus 2. X minus of minus 2 is x plus 2. So our center is x naught equals to minus 2. Then, what are we told? We're told that it converges at x equal to 4. So on this picture, over here, f of 4 converges. So that's a point of convergence. What was our basic guiding theorem is that domains for power series are rather boring. They come in open intervals or closed intervals or clopin or opposed intervals, right? Them's your choices. Or the whole real line. But we know it's not the whole real line because we're also told what? It diverges at 5, right? So think about that. What does that say? What's the largest IOC possible? The largest IOC possible cannot get past that divergence, right? If you find a point of divergence, think about the theorem, then everything past the point of divergence also diverges because it just makes the series bigger or more ill-behaved, right? So this point cannot be included, nor can anything to the right of it. So, like that, the largest IOC possible. That's as far as I can go over there, right? So if that's as far as I can go over there, that's how far? Minus 2 to 5, that's 7. Right? That's 7 units over to there. And then what's the most points I can adjoin here? Just go the other way, 7, right? 7 from minus 2 takes me to where? Minus 9, right? And then I'll ask you the question, if I want it to be the largest IOC possible, do I fill in that dot or do I leave it not filled in? I fill in the dot, right? I want it the largest IOC possible. So the largest IOC possible would be that's the first place we get divergence and the other endpoint actually converges. So the largest IOC possible is in particular minus 9 included to 7 excluded. Oh, excuse me, 5 excluded. You're like, well, where's your work? I don't know if there's really work to show here. I mean, my work is the number line. You could write a paragraph saying what I just said, but in this kind of problem, I'll just accept. I really just grade the answer here, to be honest with you guys. I mean, I've explained my logic to you in words here as we're talking through it. How about the other one, part B? The smallest IOC possible. I'll do that in blue. Well, we're given that 4 converges, right? So what are we stuck with? If 4 is a point of convergence, then we're stuck with all of this. Those have to be points of convergence, because if it converges at one point, it converges everything inside of there, right? And it goes plus minus from the center. So we're also stuck with, how far was this? 6. So we're also stuck with, 6 this way, right? From the center. That takes us to what? Minus 8. If I want the smallest IOC possible, do I want to include or exclude that other endpoint? I want to exclude it, right? So the smallest IOC possible is minus 8 not included to 4 included. There you go. Like I said, this problem is easier than problem 4 because I gave you less. Problem 4, I gave you so much information. The question is, how do you use it? Problem 6, I'll work up on the front board. I have f of x. What was it? I can't hardly read. X over 3 minus x, yeah? So this brings up an important idea, which is the recentering trick. What's the recentering trick? Take your x and replace it with x minus x naught plus x naught. Do algebra. This is generically the recentering trick. It is sometimes something that can be fleshed out. It's sometimes something that is ill-advised. All right? In this problem, I think we can hack it. So let's try it. F of x, x minus 1 plus 1 over 3 minus parentheses x minus 1 plus 1. The reason I do that is to create x minus 1s. I want an expansion in x minus 1. That's the goal here, is an expansion of x to the minus 1 to the power. So, tell you what, I'll even make a substitution here just for a moment. This is u plus 1 over, what we got? 2 minus u, where u is equal to x minus 1. Maybe that'll help some of you see what I'm doing. See, once I do that, I can look for a power series in u. I can use like a geometric series idea. Factor out the 2. Like that. And then, you know, like so, which is, you know, 1/2 of u plus 1. Well, curses. Let's see, we can clean this up just a bit. This is going to be the sum, n equals 0 to infinity, of 1 over 2 to the n plus 1, u to the power n plus 1, plus the sum, n equals 0 to infinity, of 1 over 2 to the n plus 1, u to the n. So what I did was I multiplied through the half and the u to give me the first series, and then the half and the 1 to give me the second series. Do these overlap? I mean, if you look at these overlap, right? So to put these together, we should make a change of variable. Let's see here. So this one starts where? This one starts at constant terms. Where does this one start? It starts at u, right? So this one's kind of the oddball. What we're going to do is rewrite this as the sum n equals 1 to infinity. All right? And then plus a what? Well, plus 1/2. That's the constant term that I just got separated out. Now, I can rewrite this, make a substitution here. Let's say j equals to, or rather, let's say n equals to n equals to j plus 1. I guess, oh, fine. I'm sorry, guys. make a decision here eventually. I'm going to actually change the other one over here, make a j equals n plus 1 substitution in this. If I set j equals to n plus 1, what do I have? The reason I'm doing what I'm doing right now is in order to add two series, I have to make them have the same format. I can't add the series unless they're matching, like the powers are matching, the kind of powers. We'll talk more about this week. This is kind of the next bag of calculations we need to think about, bag of tricks, if you will. So if j equals n plus 1, this is 1 over 2 to the power j, and u to the power j. Yeah? Agree? That's just a relabeling of the sum. And then over here, well, to make things look the same, I could just put n equals to j on this other one. So here I've got j equals 1 to infinity of 1 over 2 to the j plus 1, u to the power j plus 1/2. So long story short, we have that f of x is equal to 1/2 plus the sum j equals 1 to infinity. What's this? What happens if I add these coefficients? What we're looking at is 1 over 2 to the j, right? Plus 1/2 of 1 over 2 to the j. Am I right? This is 1/2 of 1 over 2 to the j. Yep.
Why is that u to the j if n is just j?
Well, that's for this part. But over here, I'm making a different substitution, namely the j equals to n. These are not the same n. These are different n's in different sums. There's nothing illogical about this, except perhaps that I'm using n in two different ways in the same calculation, right? You really should object to me using n in two different ways in the step above. So you've already used n. You should use something else for the second sum, like m. If I'd written m equals 1 to infinity there, then we wouldn't be having this discussion, right? That plus that is 3/2, right? 3/2. One over 2 to the power j times u to the j, which, cleaning it up, is 1/2 of sum j equals 1 to infinity of 3 over 2 to the j plus 1. And what was u? X minus 1. There you go. That is the power series for x over 3 minus x centered at 1. Now this seems harder than it was because I just exposed you to a new calculational problem, which is relabeling of a series. That was just a quirk of the calculation here. If you really look at what I did, it's not that complicated. I just replaced x with x minus 1 plus 1 and just did the geometric series again. Like, if you really think about the global picture of what we just did, it's not that different than what we've been doing. But it is nevertheless a new thing to learn. Yes, sir?
Which j is in your final answer?
I added those together. So once I make them match, then I can add series. So we'll talk more about this tomorrow, but how can you add series? How can you multiply series? How can you divide series? In order to add them, you need to make them have the same format, like the same kind of power structure. And then once they do have the same kind of power structure, you can just add coefficients. So adding 1 over 2j to 1 over 2j plus 1 is 3/2. It's 3 over 2, and that's what I have here. It's 3/2 times 1 over 2 to the j. Let me end class with something a little bit less stressful. How do you multiply power series? So I want to multiply these series. I would like for us to find the first 3 non-trivial terms. How do you do it? So I told you at the start of all this that part of the reason we like power series is because they behave like polynomials, right? Do you know how to multiply polynomials? Distribute, right. The game here, though, is there's infinitely many things, right? So the question is, which ones do we care about? We care about the ones which are lowest order, right? So 1 times x squared is the first thing, the lowest order I can see. And then what's next? How about this? Minus x times x squared, that's third order, right? Now, x times x squared is x to the 4th, right? Is there anything, like, can we get a cubic term here? Excuse me, can we get what are the quartic terms is my question. 1, so we get a minus x to the 4th. Let me do some color coding here. This times that gives me that. But there's another way to get x to the 4th, isn't there? What is it? Right. Aw, man, look at that. So I guess we're not done yet. Right? In fact, I'm afraid my problem may be ambiguous as stated. Let me fix it since we're out of time. The first 2 non-trivial. Two. Okay, so there it is. It's x squared minus x cubed. That's it. The reason I have not written enough of the left series to be sure about the 6th power was the trouble. So anyway, tomorrow I will tell you about multiplication and division and how to add series. And that will pretty much complete the story of arithmetic on series. And hopefully tomorrow I will state Taylor's theorem. All right? So.